Hi guys, chapter 12, part 2. We're going to go over focusing on the mechanics of the contraction. So meaning we're going to go over two different levels at the cellular level, meaning the mechanics of how single individual skeletal muscle cell or skeletal muscle fiber generate tension or how they contract. And then moving on from the cellular level to the organ level. So addressing and trying to understand, discussing about how the entire muscle, a single skeletal muscle as an organ generates tension, right? So when they generate this tension, when they contract, we're going to see also factors affecting the intensity of that tension, the force of the contraction being generated is being affected by various factors, whether they're at the cellular level or at the organ level. So because of that, you see under the learning objective here, we're going to go over factors affecting tension generated by individual skeletal muscle fibers, and also factors that are being influencing, affecting the contraction, the tension generated by an entire skeletal muscle as an organ. And then the last pillar of the lecture is about not only the motor functionality, but also the brain receives, the central nervous system receives input from the muscle to have a better coordinated activity through two structures. We're going to go over this muscle spindle and then the Golgi tendon organs to basically allow the brain to monitor skeletal muscle activity and to prevent, for example, muscle tear, to prevent excessive skeletal muscle activity. So this part, the last part, is about the sensory component, information being sent back to the central nervous system, allowing the central nervous system to really know what's going on in the periphery, what's going on at the effector organ level, meaning the skeletal muscles. So that's the gist for the lecture, the second part of chapter 12. Like I mentioned during the previous recording, so on your syllabus, there's a typo. Chapter 11 is only for one recording, and chapter 12 requires two recordings. So the first recording was done previously, and this is the second and last part for chapter 12, muscle physiology. Okay, with that said, let's get this thing started with the first slide. Starting with force generated, tension being generated by a single skeletal muscle fiber, single skeletal muscle cells, right? And it's the first thing is affected by frequency of stimulation. So you have here one stimulus, and there's a lag called a latent period before the muscle responds, right? So this is the single skeletal muscle fiber. When we say twitch, it's basically one contraction. contraction. One contraction by the skeletal muscle fiber. And this is confusion, students. They say one contraction, okay, I get it. It's one cross bridge formation. No, we are talking about thousands and thousands of cross bridge formation within that one single skeletal muscle fiber. So this is you're seeing at the cellular level, the entire cell, not at the molecular level, okay? So as you can see, if you apply a depolarization, the stimulus here means you are applying a depolarization signal. And that depolarization signal, remember from the previous lecture, this is excitation, contraction coupling. So it takes time for that action potential to be formed, because when you apply that depolarization, that's the EPP, it's like the equivalent of the end plate potential. It takes time to recruit, activate the voltage sensitive sodium channel to give birth to an action potential on the sarcolemma. And it takes some time for that action potentials to spread throughout the entire skeletal muscle fiber. Because of that, there's a lag here between the stimulus and the response, which is the contraction. And once that happens, you can see there's a contraction phase getting to a maximum tension, and then the relaxation phase. What it means here is during the contraction phase, the action potential is still present, is still spreading, is still propagating throughout the sarcolemma. But as soon as the action potential dissipates, it will lead to a relaxation phase. So here, there's no more AP, no more action potential. And as soon as there's no more action potential spreading, propagating through the T-tubule, the sarcoplasmic reticulum reclaims calcium, sequester calcium, meaning calcium will go back inside the sarcoplasmic reticulum. Without calcium, there's no cross-bridge formation. No cross-bridge formation means the muscle cell, the muscle fiber, the skeletal muscle fiber relaxes. That's one single stimulus. And when we have that single stimulus, we call that a twitch. You can have an isometric twitch or isotonic twitch. Isometric means the cell is contracting or the muscle is contracting without changing the length of the skeletal muscle cell or skeletal muscle as a whole, the entire organ. Isotonic, so meaning isometric means the muscle is shortening. This muscle, the muscle tissue, meaning the skeletal muscle cell or the skeletal muscle as an organ, becomes shorter. The length decreases. No, I take that back. The length remains the same. Isometric means the same length. Iso means the same. Metric means length. So when we say isometric, the length of the skeletal muscle cell or fiber or the length of the skeletal muscle as an organ remains the same. When we have isotonic twitch or isotonic contraction, the skeletal muscle fiber, its length decreases, or the skeletal muscle as an organ shortens or decreases, isotonic. So when we have isotonic, it means that the load can be moved by the muscle contraction. Isometric, the load is greater than the tension being generated by the muscle. Therefore, the muscle will not be shortening. The muscle is basically remain the same. So isotonic means when you're lifting an object, right? When the object can be moved by you, by your skeletal muscle contractions. Isometric means the object cannot be moved by your skeletal muscle contraction. So let's say you're pushing against the wall, your skeletal muscle are undergoing isometric contraction. When you lift a chair, your skeletal muscle are undergoing isotonic contraction. So that's the difference between isometric and isotonic. And a twitch is just one single contraction. The next one is called a TREPPI. This is an observation, but the exact molecular mechanism is still not clear to science. And let me explain. You have a capability in skeletal muscle tissue that's remarkably unique. You apply a stimulus, the muscle respond, and you let it respond, and you let it come back to rest. And you apply the same stimulus, meaning the same, so all these stimuli have the same intensity. Nothing changes. You apply to the same muscle, you have the same intensity, you have the same amplitude in terms of stimulus. The depolarization, the amplitude of the depolarization is the same. So the first stimulus generates this much tension. You let it come back, you apply the same intensity, the muscle responds by generating much more tension here. Let it rest, apply the third stimulus, the muscles generate still greater tension, despite the fact that you did not increase the strength of the stimulus. And by the fourth application, it peaks out. So this is the plateau here. Right, so this is the first application, the second application, the third application, and by the fourth application, the fifth application, the sixth, and the seventh is not shown, but it plateaus out. And we don't really understand what's going on inside the muscle, right? There are a lot of theories advanced, put forth, but there's no accepted theory to explain this observation that we call TREPPI. So the same intensity of stimulus applied to a muscle with subsequent application, the muscle can increase its tension without the benefit of an increase in the amplitude of the stimulus. So for whatever reason, the cross-bridge formation becomes more effective. The muscle becomes more efficient in terms of generating these cross-bridge formation and in generating this tension being generated, the force of contraction being generated. But we don't really understand what's going on with this concept, with these observations, or we call TREPPI. And the next one is the summation. So when the muscle contracts, they can added to one another. So this is a single contraction, so the twitch. Summation, so you have a jerky movement in your limbs. So that's summation. The next level is incomplete tetanus. This has nothing to do with the tetanus as a condition. When you take microbiology, you're going to be taught about this. This has nothing to do with the pathogen causing tetanus. So incomplete tetanus would give you shaky, really shaky movement, like if you try to break dance, that would be generated by using, in this case, you're voluntarily generating incomplete tetanus. And then the complete tetanus means the stimulation is so close in time that the contraction basically become fused into one continuous contraction. And this is what gives rise to smooth body movements, the complete tetanus. Smooth body movements, right? SBM, smooth body movements. So it allows you to do martial arts. It allows you to do beautiful ballet dancing moves. It allows you to move, flawlessly into a room, things like that. So any movement, the daily movement that generates smooth motion is due to this complete tetanus, because of the fact that the stimuli are coming so close in time that the contraction literally added up one another into one smooth contraction. So force generated individual fibers, the second factor, the diameter of the cell, the diameter of each skeletal muscle fiber dictates the tension that skeletal muscle fiber, skeletal muscle cell can generate. So the larger the diameter, the stronger the generated tension. The smaller, the slender the skeletal muscle fiber, the weaker the tension being generated. The reason is, if you have a large diameter, what it means is inside that skeletal muscle fiber, the sarcoplasm, it contains much more myofilaments. It contains much more the thick and thin filaments. It has much more myosin heads and actin protein for cross-bridge formation. So more thick and thin filaments means much more cross-bridge formation capability. More cross-bridge formation, more traction, more tension being generated. Therefore, the cell will generate much more forceful contraction, right? So the diameter is crucial for the amplitude, the intensity of the tension, the force of contraction. So again, this is the action potential, and this is the response. Okay. So again, one more time, the bigger the cell, meaning the width of the cylinder, because the skeletal muscle cell is like a cylinder, right? The larger the diameter, the stronger the tension being produced. That's the second factor, the diameter of the skeletal muscle fiber. The third factor is crucial. This is a concept that you might be taught in anatomy, because I do teach this concept already in anatomy to my students. If you take Bio 31 with me, this should be review for you. There's one typo here that I keep forgetting of changing. This is not 80, this is 100. So the range is between 100% to 120 down here. So within this range, you will have maximal tension. This 100%, this is max tension. So if your skeletal muscle fiber at rest before it contracts, and its length, it's anywhere from 100% of its normal resting length or slightly stretched out to 120 of its resting length, it will be able to generate maximal tension, maximal force of contraction. If the resting length of that skeletal muscle fiber falls out of this window, 100 to 120, so meaning if it's in this area, shorter than its resting length, or it's being overstretched more than 120, tension drops and drops quickly. Okay, tension will drop, tension also drops. So meaning the force being generated will decrease if the length of the muscle before it contracts falls between 60 and 100, or being stretched out beyond 120. Either case, both case, it will generate tension that will be less than 100%. That's exactly what you're seeing here. All of that is below 100%, right? The reason is simple. If you are stretched out, meaning this is the extreme here, there's no cross-bridge formation possible between myosin and actin. So this is a muscle that has been overstretched completely. So there's very little cross-bridge formation possible. The other extreme is when it becomes too short, the actin, the thin filaments on this side, will crash into the filaments on the opposite side. So there's a frontal collision here between the thin filament on the left side and the thin filaments on the right side. When both of them move toward the M line within the sarcomere, they're gonna butt head with one another. So as soon as the thin filaments are basically coming in full contact frontal collision, the sarcomere can no longer shorten. Cross-bridge formation will stop, right? So because of that, tension will drop, right? So, and the beauty about this is the skeletal muscle are arranged. This is another concept from anatomy, is the way they are designed. Skeletal muscle originate their origins and their insertions mostly into bones. It's also possible that muscle can insert into skin and also other muscles, but by and large is the bones, the skeletal system that basically acts at anchoring the skeletal muscles. Because of the O's and I's, origins and insertion of the skeletal muscle with the bones, they are forced always, when they are resting, they're always between 100% and 120% of their resting length. So when they contract, due to their connections, the skeletal, musculoskeletal system, they can always generate maximal tension. The reason why I say this is because when we talk about cardiac muscle, that's another story. Cardiac muscle is opposite. Cardiac muscle, contractile cardiac muscle, meaning the cardiomyocyte, at rest, they are not at the optimum resting length. So at rest, they cannot generate maximal force. When they are stretched out, then they can generate maximal force, because when they're stretched out, they will go to that optimal length between 100 and 120, and then they can generate maximal force. And this is serving another purpose. When the heart is filling with blood, incoming blood will stretch their wall, meaning it's going to stretch out the heart. And by stretching out, you're basically allowing the cardiac skeletal, cardiac muscle fiber to stretch out to their optimal length, and then they contract. And when they contract, they can generate maximal tension. They can basically efficiently pump blood out of the heart. So we'll come back to that concept when we talk about cardiac muscle fiber contraction. So this is for factors affecting single individual skeletal muscle fibers or single individual skeletal muscle cells. So this is at the cellular level. We're going to move on to the organ level on the next slide. So now we are talking about the entire skeletal muscle. This is the organ level. So again, there are three factors that can basically affect the tension generated by the entire muscle. The concept is called recruitment. So meaning how many motor units have been recruited, how many motor units have been activated, right? So we learned this already in the motor unit. Each motor unit consists of one lower motor neuron innervating X number of skeletal muscle fibers. So smallest motor unit, one lower motor neuron innervating between 2 to 3 skeletal muscle fibers. The largest ones are a single lower motor neurons innervating up to 4,000 skeletal muscle fibers, right? So that's the concept of motor units. And then we apply that concept here. So when the nervous system wants to move a limb, wants to contract a whole organ, one skeletal muscle, like the quadriceps femoris, the muscle group, it can dictate, it can decide how many motor unit it can activate depending on the strength that it wants to generate, right? So depending on the strength that you want to kick someone, your primary motor cortex can do that, can literally recruit a defined number of motor unit depending on the tension that it wants to generate. So it shows you here motor unit X and motor unit Y. And it also shows you that this is symmetrical innervation, so it's not like random. And we talk about this concept too. It allows the muscle to contract in a uniform fashion. So you don't want, half the muscle contracting and the other half is flaccid, right? So we might have a problem with that. So when the muscle contracts, it contracts uniformly throughout the muscle as much as possible. And the recruitment means increasing the number of active motor units. This is how the nervous system works. It will activate the small motor unit first, always. So the motor unit that innervates the lesser amount of skeletal muscle fiber, and it moves up. So that's what you see here. Motor unit X is smaller because it only innervates 5 skeletal muscle fiber. And then the next level recruitment is it's going to recruit the motor unit Y, which is slightly bigger because the motor unit Y now innervates 7 skeletal muscle fibers. And if you add them up, now you are recruiting a total of 12 skeletal muscle fibers. In other words, the way our nervous system is wired, it's not possible to innervate motor unit Y without innervating motor unit X. So under normal conditions, under normal healthy conditions, you should not be able to innervate, selectively mobilize motor unit Y without mobilizing motor unit X. Unfortunately, that's not how it works, right? You can mobilize, you will always mobilize motor unit X first. This happens first because it's being smaller. And then if you need more tension, then you will go on to recruit motor unit Y, which is being the second unit being mobilized. And if you need still more, you will recruit a third motor unit, which is even larger than motor unit Y. Okay. So recruitment, the more motor unit being recruited, it will generate the greater tension by the muscle as an organ. So that's what I mentioned briefly earlier, the size principle. Motor unit varies in size. So the smallest one is being recruited first, followed by the middle one, and followed by the third one. So X, Y, Z. Z is being the smallest motor unit. X is being the smallest motor unit, and Z is being the largest motor unit. W here is the upper motor neuron, okay? That's nothing new. We learned that also. Let's make sure that we have it down here. So W, which is the neuron in purple, I hope it's purple, that's the upper motor neuron. So W, that's the upper motor neuron, right? U for upper, M for motor, N for neuron. So that upper motor neuron. Now the cell body of that upper motor neuron, this cell body here, is physically residing in the primary motor cortex. P, primary, M, motor, C, cortex, primary motor cortex, or precentral gyrus. That's the anatomical name, right? Precentral gyrus, and the functional, the physiological name, primary motor cortex. It sends its axon down. This is the pyramidal pathway, and you see the 3 lower motor neurons. X, Y, and Z three lower motor neurons. LMN. L, lower, M, motor, N, neurons. 3 lower motor neurons. And their cell body of these lower motor neurons, you should know them by now. Here, if it's in the spinal cord, because it can be in the brainstem, but if it's in the spinal cord, they are physically located in the anterior gray horn of the spinal cord. A for anterior, G for gray, H for horn. So anterior gray horn of the spinal cord, or the ventral gray horn of the spinal cord. But I mentioned that already. Humans, we walk on 2 limbs, right? So anterior is more appropriate. If you describe a dog which walks on 4-leg animal, then ventral would be more appropriate, right? So in the case of human, this is human physiology class, so learn that as anterior gray horn. And then these are the effector organs. 1, 2, 3. So here you have 3 skeletal muscle fibers. Down here you have 1, 2, 3, 4, 5. 5 skeletal muscle fibers. Slightly larger motor units. And the last one, 1, 2, 3, 4, 5, 6, 7 skeletal muscle fibers. And if you look closely, the size principle is not only the number of muscle fiber that increases, but also the fiber themselves have larger diameters. Right? So larger motor units, they have 2 things. And this is new, you haven't learned that yet. Larger motor units means they have a greater number of skeletal muscle fibers per motor unit. And in other words, the larger motor units, meaning the lower motor neuron, innervates 4,000 skeletal muscle fibers. But these skeletal muscle fibers have large diameters. If you are having a lower motor neuron innervating like 3 skeletal muscle fibers here, right? These skeletal muscle fibers have slender, thin, small diameter. So they generate weak tension, but they are exquisitely accurate. So when you do a surgical procedure, you want to mobilize small motor unit like motor unit X. But if you want to kick a football like 60 yards downfield, then you might want to mobilize large motor unit like motor unit Z here that can innervate up to 4,000 skeletal muscle fibers. Right? So that's basically called size principle. So that's the second factor. moving on to the third factor. There are different types of skeletal muscle cells, skeletal muscle fibers. They exhibit, meaning they have different speed at which they can contract. So we call that differences in speed of contraction. So fast fibers, slow fibers. So again, one more time, isometric. Iso means the same. Metric means length. So without change in length, that isometric, right? So iso means the same. Same means without change. Without change means the same. And that's the iso. And metric means length. So the contraction will not generate a change in the length of the skeletal muscle as an organ. So as you can see here, different muscles responding to the same stimulus in terms of intensity. All of them go through a lag period. They all get to maximal tension. That's not the point. The point is how much time did it take them to get to maximal tension? That's how we define speed, right? Speed of contraction is the time that's that much time that it takes the extraocular muscle to contract. These extraocular muscle, those are basically 6 skeletal muscle that are basically inserting into your eyeball, right? The superior rectus, inferior rectus, medial rectus, lateral rectus, superior oblique, inferior oblique. Remember those in anatomy? So they are called extraocular. Extra means outside, right? So extraocular. So they are basically inserting into the eyeball and moving that eyeball. So so basically they're moving the eyeball because the eyeballs have the, how will I say this? One of the most important, if not the most important special senses that we have, vision. So they are extremely fast. So that's why visual reflex are also fast, right? So you can move your eye very quickly because of this, the speed at which these extraocular muscle can contract. And then the same concept, if you apply to the gastrocnemius, which is the calf muscle, posteriorly in your leg. So the calf muscle takes slightly longer time to get to maximum tension. You can clearly see that's lower than the extraocular. And finally, if we apply the same concept all the way to here, that's the soleus. The soleus is deep to the gastrocnemius, also posterior located in your leg, meaning we are behind the tibia, right? Your leg bone, tibia and fibula. That's the soleus. So much slower. It takes much more time to get to the maximal tension. So depending on the type of fiber the muscle contains, dictates it how fast, how quickly as an organ the whole muscle can generate maximal tension. So this table here, we will be focusing on, we're gonna eliminate this. And I know that you have, this table, right? But you need to understand, don't memorize it. So let's go over this. The slow oxidative or red fiber versus the fast glycolytic white fiber. Pay attention to the word, like call it, this is using glycolysis. So not requiring oxygen, right? So here, no oxygen. So if you don't need oxygen, you don't need a lot of mitochondria. So if you go down here, mitochondrial density, low. If you don't need oxygen, you don't need blood vessels perfusing your muscle. So capillary density, low. If you don't have oxygen, then you don't really need proteins that stores oxygen for you. Myoglobin content. That's a protein that stores oxygen in muscle, low. Okay, so those, whereas, so if you don't have no oxygen, you can do oxidative phosphorylation. So oxidative capacity, low. And since you are relying on glycolysis, high glycolysis. And these are characterized by speed of contraction really quickly. Both of them are fast and high with the myosin head. Myosin activity, ATPase activity are extremely quick. Okay? However, they fatigue very easily. So resistance to fatigue, low, meaning they cramp out quickly, right? They fatigue very fast. Diameter size and motor unit size when you generate speed to contraction here, quick, and so they have a tendency to be large. So they generate also powerful tension. So force generating capacity also high. Okay? So that's how you learn, understand. And now the opposite over here. So over here, oxidative means requiring oxygen, right? To oxidize fuel molecules. So you need a lot of mitochondria. So you have high mitochondrial density. If you need a lot of oxygen, you need a lot of delivery of oxygen. So you need a lot of blood vessels. So capillary density is also high. If you need oxygen, then you need a way to store oxygen. So myoglobin content is also high. And myoglobin is like hemoglobin. It contains the heme group, iron, makes it gives the tissue a reddish color. That's why blood is red. That's why the meat, the oxidative, relying oxidative phosphorylation or slow oxidative meta, metab metabolic pathways, they appear red. So we call it red meat. Whereas over here, you have very low myoglobin. That's why the tissue, the muscle tissue, appears whitish, right? So all the white meat, like pork, chicken, and all that, is because they have a low myoglobin content. Whereas beef, the red meat, they have a high myoglobin content. And if you do aerobic cellular respiration, you are resisting fatigue. So your muscle, it's harder for your muscle to cramp. So you have a high resistance to fatigue. They have a tendency to be small in size, both the motor unit and the diameter of the muscle fiber. And because of that, they have weak tension generating capability, so low. And also they have a little myosin activity, so low here, leading to slow speed of contraction. And they need oxygen, so they don't have they don't rely on glycolysis, so it's low. And oxidative capacity is extremely high because here it requires oxygen. Okay, so that's how you understand the concept instead of blindly memorizing everything. Moving on to the last part of the lecture, this is how the effector organs communicates with the central nervous system, allowing coordinated motor responses, allowing coordinated skeletal muscle activity. So rely on two structures. Let's start with the muscle spindle. We've learned so far, what we've been paying attention to is only one type of skeletal muscle fibers, the extrafusal fiber. This is the muscle that contracts, right? And they are innervated by the alpha motor neurons. So the lower motor neurons that we've been talking about, we are referring to them as alpha motor neurons. But there's another type of lower motor neurons, and they are called gamma motor neurons. And what is important is both the gamma and the alpha are synapsing with the upper motor neuron, the same upper motor neuron, upper motor neuron will synapse with both of them. Okay? So, since the alpha motor neurons have a larger diameter in terms of axons, they're going to propagate the action potential faster than the gamma motor neurons. So when the upper motor neurons fires an action potential, sending out a motor command to contract a muscle, the extrafusal fiber always contracts first. Because the gamma motor neuron, what they basically innervate is not the extrafusal fiber, they are innervating the intrafusal fiber. And these guys, their job is not to contract the muscle as a whole. Their job is to basically contract in such a way that it reflects the status of contraction as the entire organ. So the muscle spindle is a sensory organ, if you will. So it detects the length of the muscle as a whole, and it sends that information back to the central nervous system. So if the muscle is contracting and the gamma motor neuron is not responding, then the muscle spindle will not be able to detect the length, the change in length of the entire organ. So when the muscle contracts, we learn this as an organ, right? The entire muscle becomes shorter. So as the length of the skeletal muscle as an organ decreases, that length decrease, that length change needs to be sent to the nervous system, needs to be sent to the central nervous system. Right? So the only way is, so what's going to happen is when the extrafusal fiber contracts, because the gamma motor neurons propagate action potential faster, the alpha motor neurons propagate action potential faster than the gamma motor neurons, because the axons on the alpha motor neurons are larger in diameter, and in terms of myelination extend also. So action potential travels propagated faster on the axons from the alpha motor neurons than on the axons of gamma motor neurons, even though they receive the same signal from the upper motor neurons. So there's a slight delay, a fraction of a second later, a few milliseconds later, that the skeletal muscle, the extrafusal fiber contract, the intrafusal fiber also will contract to follow the length decrease. It's allowing the spindle to detect muscle length in change. So as the intrafusal fiber contracts, it sends afferents, meaning axons that are basically conveying information toward the central nervous system. So they are transmitting sensory information back to the central nervous system, allowing the central nervous system to monitor the length of every single skeletal muscle. Right, so the afferents are type 1A and type 2 afferents. So you're going to learn that as is described over here. So I just explained the concept. So detecting length change in a muscle by using these sensory components, and they detect the intrafusal fiber contraction due to the contraction as the entire muscle. So depending on the shortening, the extent of the shortening of the intrafusal fiber, that shortening is detected by sensory afferents. And they detect the length change. And this length change, that's by the intrafusal fiber, not extrafusal. Extrafusal is the contractile skeletal muscle fiber responsible to contract the entire organ, right? So the extrafusal fiber are not part of the muscle spindle. They have nothing to do with the sensory component notification back to the central nervous system about the status or the length status of the entire organ. The other one is located, this one, the muscle spindle is located within the muscle itself. The next one is located in the tendon, which is also part of the skeletal muscle. The tendon is attaching the muscle, the skeletal muscle, to a bone. We call it a tendon. On the next slide. The Golgi tendon organs. And this system, the Golgi tendon organs, inhibits a reflex. So as the muscle is stretching out, the reflex is to contract. But under some circumstances, when that muscle is contracting so forcefully or stretched out so forcefully, if you contract, you will tear tissues. And by the way, what is amazing about this is that tendon, the insertion here, is so strong that if anything breaks, it's the bone. So if you have excessive activity, most likely you will not be able to tear the tendon away from the bone, but the force will fracture the bone, right? So to prevent any tissue injury, whether in the tendon tear or the bone fracture, this Golgi tendon organ will inhibit the reflex arc that will basically, under normal circumstances, will contract in response to any excessive muscle stretch. So it detects the muscle tension and it basically prevents excessive activity, preventing tissue injury in at that particular connection between the muscle and the bone. So between the muscle and its insertion or its origin. Oftentimes it's the insertion because the origin doesn't move. And we learn that from anatomy. So when the muscle contracts, the origin remains stationary. The bone that moves is the bone that resides at the insertion. So when the muscle inserts into a bone, it will move that bone. But when the muscle originates on a bone, the bone that the muscle originates remains stationary. And this will end the second part of chapter 12, today's recording. And until the next recording, be safe out there, be healthy, study well, and I will see you during the next recording. Take care until then.